Students, so today we are going to our chapter towards organic chemistry of the first year. So we are dealing with the first chapter of organic chemistry, that is organic chemistry, some basic principles. So in this chapter of organic chemistry, some basic principles, we already know the organic chemistry is a branch of chemistry which deal with the study of hydrocarbons, that is carbon and hydrogen. The organic compounds or the hydrocarbon are basically classified into three: alkane, alkene, alkyne. If it is alkane, they are single bond. The equation is CnH2n plus 2. If it is alkene, it is double bond. The equation is CnH2n. And if it is alkyne, that is triple bond, the equation is CnH2n minus 2. So these are the classification of hydrocarbons. So the hydrocarbon or the organic chemistry is classified into three: alkanes, alkenes and alkynes. If it is alkane, equation is CnH2n. Alkene, the CnH2n plus 2. If it is alkene, the equation is CnH2n. And if it is alkyne, the equation is CnH2n minus 2. Is that clear? Now see here guys, why these organic compounds is majorly formed. The organic compounds is majorly formed due to the catenation property of the carbon. What is meant by catenation is the self-linking property of carbon is known as catenation. If two carbon atoms join together, it is known as ethane. If it is three carbon atoms joined together, it is known as propane. If it is four carbon atom, it will be bute. If it is 5, it will be pent. If it is 6, it will be hex. If it is 9, it will be nonane. Is in that way, this is a catenation property. The self-linking property of this organic compound is known as a catenation property. So first of all, we are going to study about what is meant by homologous series. Generally, we can say that a series which differ by CH2 bond is known as a homologous series, or we can also explain a series of organic compound each containing a characteristics functional group form a homologous series in which each members are differ by CH2. So it consists of a functional group and it will be differ by CH2 bond, can be defined as a homologous series. In this homologous series CH2, so the total atomic mass carbon 12 and 2 hydrogen, that will be equal to 14 unified atomic mass. So this phenomena is known as the homology. This phenomena is known as a homology. So now we discussed about a homologous series. We can explain a homologous series as a series in which differ by a CH2 bond, which will have a characteristics functional group. So they can be also defined as a members. They are differ by a atomic mass of 14. So this phenomena is known as a homology. Is that clear? So now we discussed about what are the classification of organic compounds and what is meant by catenation and what is meant by homologous series. Let us go to one of the question of Neet question. It explains about the classification of the organic compounds. The organic compound is majorly classified into cyclic and aliphatic, that is aromatic and aliphatic compounds. In this aliphatic itself, in aromatic also, it is classified into heterocyclic and homocyclic condition. So you have to know what is meant by homocyclic and heterocyclic condition. In heterocyclic, it consists of any other element than carbon. It may be sulfur, nitrogen, oxygen. In that any elements are present, that is known as heterocyclic. In homocyclic, it only contain the carbon and hydrogen only. For example, if I am writing cyclopropane, cyclopropane I can write like this way. Exactly. The furan in that type of things is an example of heterocyclic because it consists of other types of elements is known as a heterocyclic compounds. If it is cyclohexane or a cyclohexene, everything are the example of a homocyclic condition. If it is heterocyclic, it consists of other than one element, that is maybe oxygen or anything like that, oxygen, sulfur, anything. So you have to keep it in mind what is meant by homocyclic and heterocyclic. Is that clear? So the heterocyclic, you can do some of the examples. The heterocyclic examples are, the first one is furan. Furan, what is furan? How can you represent furan? Furan can be represented like this way. This is known as furan. Okay, furan. Okay, so furan is an example of a heterocyclic compound because it consists of an element other than carbon and hydrogen is known as a heterocyclic compound. There are many examples regarding with the heterocyclic compounds. You can use thiophene. Thiophene is, instead of this oxygen, it will be sulfur. This one is known as a thiophene. This is known as a thiophene. So instead of oxygen you are using sulfur, it is known as a thiophene. And also pyridine. Pyridine is very simple, that is, it will be like this same thing. Instead of you have nitrogen in this group, this is known as pyridine. So furan, thiophene, pyridine are the examples of heterocyclic compounds. So what are the heterocyclic compound? The compound which consists of any other element than carbon and hydrogen is known as heterocyclic, and if a compound consists of only carbon and hydrogen, it is known as a homocyclic. In the condition, there is a question is given: a compound with a molecular formula C4H4O has all 4 carbon atoms and oxygen atom in a ring. So if it is a ring like structure, so it will be aromatic. It's clear. Aromatic means it will be cyclic ring. Is that clear? Then it is also has 2 double bond. If it is 2 double bond with aromatic, 2 double bond alternately, it can be said that it is known as aromatic. Is that clear? Then the compound is, that's the question. So you have seen that there is an oxygen is here. If there is an oxygen is here, it can be form a compound like there is an oxygen also. So it may be it will be heterocyclic because there is another one element than carbon and hydrogen, therefore it should be heterocyclic. And also it is aromatic because it will have 2 double bonds is there and there is only 4 carbon atoms, so alternatively there will be double bond will be there, and also it is a ring like structure, therefore it will be cyclic in structure, therefore it is aromatic. Also there is a element than 1 oxygen, so which will be the answer? If it is homocyclic, no, it will not be homocyclic, it is aromatic, it will be right. The next one, the condition is it is heterocyclic and aromatic, it will be quite right because it is heterocyclic, that is that have an element than the carbon and hydrogen, and it is aromatic in condition, therefore the answer will be heterocyclic and aromatic. Is that will be homocyclic? No, it will not be homocyclic, it will be heterocyclic but not aromatic. It is also wrong because it is heterocyclic but it is aromatic also. So the answer will be heterocyclic and aromatic. That's why you should know what is meant by homocyclic and heterocyclic. The heterocyclic, keep the examples with you. The first one I said that it is furan. Furan means this consists of 1 oxygen, this one is known as furan. And the same thing, if instead of this oxygen you have sulfur. Instead of this oxygen, if you have this sulfur, it is known as a thiophene, and this one is known as a pyridine. This one is known as a pyridine. Is that clear? These are the examples of heterocyclic compounds. Is that clear? Now we are leading to some of the questions regarding to IUPAC naming, that is based on nomenclature. So students, now we are dealing with some of the problems related to IUPAC namings. Let us look at the first question. It was a question is given here. So I am giving the more priority for the oic acid. So numbering should be start from here. 1, 2, 3, 4. So this which will be the correct answer. See here, the first one, that is the 4th carbon is isocyano. Is that right? Yeah, it's right. That is 4 isocyano, and this is a benzene with oic acid, that is benzoic acid. So which will be the correct answer? A will be the correct answer, that is 4 isocyano benzoic acid. Is that clear? This will be 4 isocyano benzoic acid. Is that clear? Let us go to the next question. In this question, I am numbering starting from the more priority for the double bond. So I am giving from number from here 1, 2, 3, 4, 5, 6. Okay, so while doing numbering from this side, this is a branch here, another branch here, another branch here. So we can say 1, 3, 3. There is 3 branches. So 1, 3, 3 try. There is 3, that is trimethyl. This is cyclohex because 6 carbon with the first carbon having double bond, cyclohex 1 ene. So we can say that 1, 3, 3 trimethyl cyclohex 1 ene will be the answer. Let us look, that will be here or there. Yeah, it will be here. That is 1, 3, 3 trimethyl cyclohex 1 ene. Is that clear? Let us go to the third question. In this question, I am giving the number from this side 1, 2, 3, 4. Then only you will get the answer with respect to the given options. So given the first one, methyl 2,2 acetyl ethanoate. Methyl 2,2 Where is methyl 2,2? There is nothing like that, so it will be a false thing. Second one, 2,2-acetyl 1-methoxyethanate, which will be methoxy. There is nothing methoxy here, so it will be also wrong. So the first one will be wrong, second one will be wrong. The third one we can do, see here, methyl, it will be that methyl 2-acetyl, that is 2-acetyl 3-oxo, this is butanate, it will be right. Is that clear? It will be quite right. So we can say that it is methyl 2-acetyl 3-oxo butanate. It will be right. So it will be the correct answer. Is that clear? So the answer will be C, will be the answer. So we discussed some of the higher order questions regarding to the IUPAC, and while doing the IUPAC you have to also find the hybridization type questions. For example, if a question come like this, state the hybridization of C2, C3, C4, C5, C6. If a question come like this way, you have to find the hybridization. I make you to study that hybridization is equal to number of sigma bond plus the lone pair of electrons. Number of sigma bond plus lone pair of electron. In the second carbon, there is a 1 sigma bond and a 2 pi bond is here. And here is another sigma bond. So hybridization is equal to, there is no lone pair of electron. There is 2 will be the answer here. That is 1 sigma bond, 1 sigma bond. That is sigma plus sigma is equal to 2 sigma. So it will be equal to sp hybridization. So here will be, it will be sp hybridization. Is that clear? Is that clear? In the third carbon, see here 1, 2, 3. There is 3 sigma bond here. 3 sigma bond, and also there is 1 hydrogen is here. So I am doing this hydrogen like this way. There is another also sigma bond. There is 1, 2, 3, 4 sigma bond is here. If it is 4 is the value, what will be the hybridization? sp3 will be the hybridization. Is that clear? If 2 is the value, it will be sp. If it is 3, it will be sp2. If it is 4, it will be sp3. If it is 5, it will be sp3d. If it is 6, it will be sp3d2. If it is 7, it will be sp3d3. See here, if in this condition, the first carbon, it consists, see here, in the first carbon, it consists of 1 sigma bond, 1 sigma bond, 2 sigma bond, therefore it will be sp. In this condition, there is also 1 hydrogen here, 1, 2, 3, 4 sigma bond, therefore it will be sp3 hybridization. Is that clear? Next one, let us look, this is the first carbon, second carbon, third carbon, let us look the fourth carbon. In this fourth carbon, 1 sigma bond is here, another 1 sigma bond is here, another hydrogen also here. I am putting this hydrogen like this way, therefore there are 3 sigma bond is here. If it is 3 is the value, what will be the hybridization? sp2 will be the hybridization. So now you got sp, sp3, sp2. Now let us look the fifth carbon. Sorry, which carbon you are asking? Sixth carbon. So the sixth carbon, is here. This is a sigma bond, this is a sigma bond, this is a sigma bond, and this is a sigma bond. There is 4 sigma bond, therefore here will be sp3 will be the hybridization. So now you got sp, sp3, sp2, sp3. This will be the hybridization. What is hybridization? sp, sp3, sp2, sp3 will be the hybridization. It is the answer of this question to find the hybridization. This type of question is previously asked for different types GIBMER and that type of questions, and also now in 2020 you only have one and only NEET exam. It is also extended, so go through this type of questions and study it very well. Now we are dealing with isomerism. So generally you have to know isomerism is 2 or more compounds possess same molecular formula but different properties is known as isomerism. So I am giving you a table of isomerism. So isomerism is classified into 2, that is structural isomerism and stereoisomerism. Structural isomerism having same molecular formula but different structure formula, and stereoisomerism have the same molecular formula and structures but different in their arrangement is known as the stereoisomerism. The structural isomerism is further classified into different types, that is chain isomerism, position isomerism, functional group isomerism, metamerism and tautomerism. And stereoisomerism is classified into 2, that is geometrical isomerism and optical isomerism. If it is geometrical isomerism, there are cis and trans. If it is in the both side, it is known as cis. If it is in the opposite side, it is known as trans. And the optical isomerism is dextro-rotatory, that is clockwise rotation, and levo-rotatory, that is anti-clockwise rotation. And what about the examples of chain isomerism? What is meant by chain isomerism? That having same molecular formula but different structural formula during their chains. Example, we can say that 2-methyl butane and pentane is an example of a chain isomerism. And if it is position isomerism, that different their positions. Example, but1 ENE and but2 ENE is example of position isomerism. Next, functional group isomerism, they are different in their functional groups. For example, that is having same molecular formula. That is, we can give an example, that is propanol and propan 2-1. Propanol having aldehyde group and propan 2-1 having keto group. Metamerism, what is meant by metamerism? Having different alkyl groups, having different alkyl group on the either side of the functional group. It will have a different alkyl groups on the either side of the functional group is known as a metamerism. The example is the pentan 2-on and the pentan 3-on. I am given here, it is an example of metamerism. And the last one, it is given here, that is tautomerism. Tautomerism example I am given here is ketoenol. Ketoenol, what is the condition of tautomerism? That is, that arises due to migration of hydrogen atom from the polyvalent atom to the other. That is condition of this is the condition of tautomerism. The example I am given here is ketoenol. Go through the examples and post sometimes and write these all things. Okay. We will go to the next topic. Now we are dealing with some of the reaction mechanisms. So first of all, we are dealing with the homolytic fission, and now we are dealing with the heterolytic fission. These are the two fissions we have to discuss, that is homolytic fission and heterolytic fission. It's very simple topic. Homolytic fission is a symmetrical cleavage. The symmetrical cleavage is, we see here, this is two atoms here. This electron will go to here and this electron will go to here in the presence of heat or light. So it will become a alkyl free radical or halogen free radical. In the case of heterolytic fission, I said that in the heterolytic fission it is unsymmetrical in nature. In this condition, for example, if it is CH3X is given, where X is most electronegative, this is more electronegative, this whole electron will go to this X, that will become this X minus, this will become CH3 plus. In the same example, if the C is most electronegative than this element, that is Z I am given here. So all the electron will go to this CH3, it will become CH3 minus and Z plus. So the whole electron will go to one side is known as the heterolytic fission. If it is symmetrically distributed, it is known as the homolytic fission. And if it is unsymmetrically distributed, it is known as the heterolytic fission. Is that clear? Now let us look on what is different types of attacking reagent. The attacking reagents are electrophile, nucleophile and amphiphiles we have to study. Electrophile are actually, they are positively charged or neutral charged things having electron deficient atoms, so they have a tendency to accept the electron, therefore it can act as a Lewis acid, that is electron pair acceptors. And in the case of nucleophile, the nucleophile are negatively charged, and even though if it is negatively charged or neutral molecule having, they are electron rich, therefore they have a tendency to donate the electrons. So they can act as a Lewis base and this will act as a Lewis acid. You have to keep the conditions very well. Electrophile are positively charged or neutral molecule having electron deficient, so it have a tendency to accept the electron, therefore it is Lewis acid. In this nucleophile are negatively charged or neutral molecule having electron rich, therefore it have a tendency to donate electron, that is Lewis base is the condition. And what is meant by amphiphiles? Amphiphiles is the thing, it can act as a both electrophile and nucleophile. So it will be amphoteric in nature, is known as amphiphiles. Is that clear? Let us look at one of the question, that is the nucleophilicity order between CH3 minus, NH2 minus, HO minus, F minus. How can you find the nucleophilicity? We said that if it is nucleophile, they are electron rich. Electron rich, therefore that as Lewis base, they have a tendency to donate the electrons. So see here, lesser the electronegativity of the donor atom. If the donor atom, if it have a less electronegativity, more tendency to give a lone pair of electron. Is that right now? If it is lesser the electronegativity is very less. If what is meant by electronegativity, it is a tendency to accept an electron. If it is electronegativity is very less, it have a more tendency to give a lone pair of electron. So it have a tendency to give an electron. Is that clear? So more it's a nucleophilicity, therefore it will have a more nucleophilicity. So they having low electronegativity will have a more nucleophilicity, because their electronegativity is less, means there is a comparatively electropositive, that having tendency to give the electron. So which will have a more less electronegativity. Carbon will have less electronegativity. We already know that electronegativity increases along the period. So carbon family, nitrogen family, oxygen family and halogens, among this carbon family have a less electronegativity, so which will have a maximum nucleophilicity. Carbon CH3 minus, is that clear? Then it will be for NH2 minus, then it will be for OH minus, then it will be for F minus. This will be the order. Is that clear? So now we discussed about the reaction mechanisms and attacking reagent. Reaction mechanism is a homolytic fission and heterolytic fission. If it is symmetrically distributed by the electron to forming free radicals, it is known as homolytic, and if it is unsymmetrical by the difference in their large difference in their electronegativity, it is known as heterolytic fission. Then we discussed about what is electrophile. They are Lewis acid, that is electron pair acceptors. Then nucleophiles are Lewis base, that is electron pair donators. So we have to amphiphile means they are act as a both electrophile and a nucleophile. Then we discuss the order of nucleophilicity. The nucleophilicity order, I said that if they are having less electronegative, that is when the electronegativity is less, that is more electropositive, they will have a tendency to give the electron. So if it is nucleophilic, it should be Lewis base, that have a tendency to donate electron. Among this carbon, nitrogen, oxygen, fluorine, which will have a more tendency to give electron, carbon will have because it have less electronegativity. Then it will be for nitrogen, then oxygen, then fluorine. So students, now we are dealing with the electron displacement effect, that is inductive effect, electromeric effect, then resonance effect and hyperconjugation. These are the different effect of electron displacement. Let us look at the electron displacement by inductive effect. It is the displacement of a sigma electron. Sigma bond is a single bond along a saturated carbon chain. It is a movement or it is a displacement of a single bond along a saturated means alkane chain. It may be electron donating or electron withdrawing. If it is electron donating, it is known as a plus inductive effect, and if it is, that is positive inductive effect, and if it is electron withdrawing, it is known as a negative inductive effect. Is that clear? So inductive effect is formed by the displacement of sigma electron along a saturated chain. If it is electron donating, it is plus, and if it is electron withdrawing, it is negative. Next one is we are discussing with the electromeric effect. The electromeric effect is formed by the transfer of pi electron. The transfer of pi electron in the presence of attacking reagent. We studied the different types of attacking reagents like electrophile, nucleophile, amphiphiles, etc. So it is a transfer of pi electron, and now it is a transfer of sigma electron. It is in the presence of attacking reagent. The transfer toward the atom which the attacking reagent attached. The transfer towards the atom to which the attacking reagent is attached, it is known as a plus electromeric effect. Then next one is a transfer away from the atom to which the attacking reagents are attached. It is known as a negative electromeric effect. So now we discussed the inductive effect and the electromeric effect. Let us go to the third one, that is resonance effect or mesomeric effect. Resonance effect can be represented by R effect. So it is defined as the polarity produced in the molecule by interaction between two pi bond. It is the polarity difference is formed between two molecules. We studied the resonance structure of different compounds during the chemical bonding chapter. So it is defined as the polarity difference between two pi bond, or a pi bond or a lone pair of electron is known as a resonance or mesomeric effect. It is a polarity change formed, defined as the polarity produced in the molecule by the interaction of two pi bond or a pi bond and a lone pair of electron is known as a resonance effect or a mesomeric effect. Then we are discussing with the hyperconjugation. It involves the delocalization of the sigma electron of a CH bond of a alkyl group directly attached to unsaturated carbon atom. What is the condition of hyperconjugation? It involves the delocalization. That delocalization means the electron is moving into a particular area. The delocalization of sigma electron of a CH bond of a alkyl group directly attached to unsaturated carbon atom. It is not saturated, that is it may be a double bond or a triple bond. The decrease in that is the hyperconjugation decrease with the decrease in the number of alpha carbon. The alpha carbon is the first carbon that is attached to any chlorine, bromine, anything that is known as the alpha carbon. For example, this is CH3, CH2, then it is tertiary, and it is this secondary, and this is tertiary. If in this condition the hyperconjugation order will be greater for methane, then it will be for ethane, then it will go for secondary, then it will be go for tertiary. This will be the order. You have to keep the order very well because it involves the delocalization of the sigma electron, sigma bond single bond in the CH bond of a alkyl group directly attached to unsaturated carbon atom. It decreases with the decrease in the number of alpha hydrogens. So when the carbon atom decreases, then the resonance effect also decreases. So it will be when the alpha carbon decreases, the hyperconjugation increases, therefore it will be higher for CH3, then CH3, CH2, then secondary, and this is for tertiary. And now we are giving you some of the note about the stability of carbocation, carboanion and free radical. If it is carbocation, the order of stability is tertiary, secondary, primary. If it is carboanion, the order of stability is primary, secondary, tertiary. If it is a free radical, the order of stability is tertiary, secondary, primary. This is the order. So now we discussed about the electron displacement, that is about the inductive effect, electromeric effect, resonance effect or mesomeric effect, and hyperconjugation. And also we explained the different type of stability, that is stability of carbocation, that is tertiary, secondary, primary, carboanion, primary, secondary, tertiary, free radical, tertiary, secondary, primary. We discussed all these things. So what is, again I'm saying, what is meant by inductive effect? This is formed by the displacement of sigma electron. So when it is electron donating, it is plus, and if it is electron withdrawing, it is negative. So if it is electromeric effect, it is a transfer of pi electron that is in the presence of attacking reagent like electrophile, nucleophile or amphiphiles. So this towards the attacking reagent it is plus, and away from the attacking reagent it is minus. And then we discussed about the resonance effect. It is formed by the difference in the polarity of two pi bond or a pi bond or a lone pair of electron, and hyperconjugation involves the delocalization of sigma electron in a CH bond of an alkyl group directly attached to a carbon atom. So we said that if it decreases with the decrease in the alpha hydrogen, that is alpha hydrogen. See here, there is, if the less number of carbon, it's first one CH3, then CH3, CH2, then it will be go for secondary, then it will be go for tertiary. This is the order, that is primary, secondary, tertiary will be the order. In this condition of primary itself, if they are having less number of carbon, it will be have a higher hyperconjugation. Then we discussed the stability of carbocation. The stability of carbocation is tertiary, secondary, primary. The stability of carboanion is primary, secondary, tertiary, and the stability of free radical is again tertiary, secondary, primary. Okay, so students, now we are dealing with some important methods of purification of organic compounds. There are different methods of purification. You can go through these purifications very well. The first one is, I'm given here crystallization. I'm giving here the order of purifications here. You can go through this purification table. So the first one I'm given is crystallization. The second one I'm given with sublimation. All things you know it very well. Sublimation is from moving off a solid to gas transformation. Then it is by simple distillation. I am given you what is meant by simple distillation. It is used to separate a volatile liquid or a non-volatile liquid. It can be used for both volatile, it is used for separation of volatile liquid from a non-volatile liquid. Then we use a steam distillation. Then we use a differential extraction. Then we use a fractional distillation. Then we use a chromatographic method. Then adsorption chromatography, column chromatography, thin layer chromatography, partition chromatography, and paper chromatography. These are the different chromatographic method is given here. Pause sometimes and go through the principles and applications of these methods. So I am giving you different methods of purification. The first one I am given with this crystallization. Go with the crystallization. What are the applications of crystallization and the applications and principles of crystallization. Then you go with the second one, that is sublimation. Then it will be by simple distillation. Then it will be by fractional distillation. Then it will be by steam distillation. Then it will be by differential extraction. Then it will be by chromatography. Then adsorption chromatography, column chromatography, thin layer chromatography, partition chromatography, and paper chromatography. Go through all the topics and make the notes very well. Students, now we are dealing with our next chapter of organic chemistry of the first year, that is hydrocarbons. We already explained that hydrocarbons are generally classified into three, that is alkane, alkene and alkyne. If it is alkane, the equation is CnH2n plus 2. If it is alkene, the equation is CnH2n, and if it is alkyne, the equation is CnH2n minus 2. So first of all, we are dealing with alkane, its preparations. We are directly going to its preparations. So during this preparation, first of all, we are dealing with addition reaction. Addition reaction, it can be also known as the hydrogenation reaction of unsaturated alkanes. For example, in this reaction, if it is reacted with the hydrogen, this double bond will breaks and this hydrogen will come to this one and this hydrogen will come to this one. This reaction occur in the presence of nickel. It will become a saturated hydrocarbon. So a unsaturated converted into a saturated hydrocarbon in this preparation of addition reaction, that is hydrogenation reaction in the presence of nickel. Okay, the hydrogenation reaction, another example we can say, the direct example we can say the preparation of vanaspati ghee is an example of a hydrogenation reaction. Then we discussed about the next reaction. See here, this is ethyne, that is triple bond. For triple bond, you have to break this two bond. You have to need, if it is only one bond, that is double bond, we need only one hydrogen. If it is triple bond, we need two H2. Then this bond will breaks and there are four hydrogen. So two hydrogen will go to this carbon and two hydrogen will go to this carbon. So it will become CH3, single bond CH3. This reaction also done in the presence of nickel. This is known as the addition reaction. That is addition of hydrogen. The second reaction is Wood's reaction that you already studied, that is Rx plus Na plus XR, that is 2Rx plus Na. This NaX, X combine each other, it will become NaX, and this R and combine each other, it will become RR. This reaction done in the presence of dry ether. This is known as Wood's reaction. So you know that now the addition reaction, that is hydrogenation reaction and Wood's reaction. In this Wood's reaction, that is Rx react with the Na in the presence of Rx, it will become RR plus NaX, and this reaction is done in the presence of dry ether. Then we discussed about a decarboxylation reaction. In this decarboxylation reaction, I am giving an example of CH3COONa react with the NaOH in the presence of CaO and heat. That is decarboxylation. So it will become, that is CH4, that is CH4. This H will be go to this carbon. So this H will be moved to this carbon. It will become CH4. Then it will become Na, that is Na2. C is here, 3 oxygen is here. It will become Na2CO3. This reaction is known as a decarboxylation. So now we studied addition reaction, Wood's reaction and decarboxylation. Then we are going to Kolb's electrolysis. For example, this is RCOONa plus H2O undergo electrolysis in the presence of electricity. So what will happen? This R recombine to form another compound, and else whatever the thing will be liberated, it will become NaOH plus H2. NaOH plus H2. So now we studied the preparations of alkane. The preparations of alkane, you study the first reaction is an addition reaction, second reaction is a Wood's reaction, third reaction is a decarboxylation, and the last reaction is a Kolb's electrolytic method of preparation. Is that clear? Go through the preparation, pause it sometimes and study it very clearly. Then we are going to the physical properties. Generally, the alkanes are colorless, odorless, insoluble in water, and soluble in organic solvent or protic solvents. Also, we can say that the boiling point, you have to find the boiling point. The boiling point is directly proportional to molecular weight and inversely proportional to branching of same alkyl group. If it is same alkyl groups like isopropyl chloride or chloropropane, so isopropyl chloride will have a less boiling point because it have a branching. So if it is chloropropane and isopropyl chloride, in the case of isopropyl chloride, what will be the chance? Isopropyl will be, it will be like this. If it is chloropropane, it will be like this, which will be have more boiling point. This one will have more boiling point because it is inversely proportional to branching, because both of them have 3 carbon and 1 chlorine. So in this condition, we have to look on branching. If the branching increases, boiling point will be decreases. Is that clear? Now we are going to the so branching increases. So branching is directly proportional to molecular weight and inversely proportional to, boiling point is directly proportional to molecular weight and inversely proportional to branching. Is that clear? Then we are going to conformers. Conformers, there shows two types of conformation that we are going to study: Sohos projection and the Newman projection. In the Sohos projection, it will be in this shape, that is, this is ethane. This is ethane. It will be Sohos projection. This is a carbon atom you are representing. These 2 points are a carbon atom. If it is arranged in the same way, that is in the same direction, it is eclipsed. If they are opposite direction, this is clockwise and this is just opposite of that, it will be known as staggered. These are differ by an angle of 120 degree. And in the case of Newman projection, it is a 2-dimensional projection, and this is considered as a 3-dimensional projection. So in this condition, it will be in the same way, they are differ by 120 degree, and it will be in the 3-dimensional structure. If it is in the same side, it is eclipsed. If it is opposite, it is known as staggered. The most stable will be staggered is most stable in the case of eclipsed condition. Or we can also say that anti-conformers, I am writing here, anti-conformers are more stable than conformers. Conformers is the anti-conformers is more stable. That's why I'm saying that the staggered condition is more stable than that of eclipsed condition. Also, we can say that another condition that what is the another name of conformers? Conformers is also known as rotamers. Okay, so you have to keep in mind anti-conformers have these more stable than that of conformers. So you can able to do the problems related to conformers also. So this now we deal with the alkynes preparations. So preparation is from addition reaction, Woods reaction, decarboxylation and Kolb's electrolytic method, and we studied the physical properties, that is colorless, odorless and insoluble in water and soluble in organic solvents. Boiling point is directly proportional to molecular weight and inversely proportional to branching. Then we studied about the conformations. Is that clear? So now we are dealing with the alkenes. Alkenes is known as the double bond. The general equation is CnH2n. So first of all, we are dealing with the geometrical isomerism. Actually, we know that we already studied the isomerism. There are stereomerism is that is the behind the stereomerism is a type is known as the geometrical isomerism and optical isomerism. The geometrical isomerism are two types, that is cis and trans isomerism. I am giving you directly the example but2-in and but2-in example. If it is but2-in, if these two carbon groups are occur and two hydrogen group are in the same side, it can be seen as cis but2-in. In this cis but2-in, this is electropositive and this is electronegative comparatively. So I am writing the dipole from positive to negative, so it will have a dipole moment is equal to 0.33 d, that is d by. D means dby. And what about that trans but2-in? This is that is two carbon group in the opposite direction. I am writing this from this carbon to this carbon and from this carbon to this carbon, and these two carbons, that is one dipole in this direction, another dipole is in the opposite direction. Two dipoles cancels each other, it will be equal to 0 in the case of a trans but2-in. In the cis but2-in, it will be equal to 0.33 d. Is that clear? So now we discussed about the cis and trans isomers. So in the cis, there is a value in between that of 0 to 1. In the case of trans, it will be equal to 0. So what's the next condition? We are going to explain about the preparations. So in this preparation, we are starting from the alkyls, that is from alkynes, that is if it is CH3 triple bond CH triple bond CH react with the hydrogen, this triple bond breaks, one hydrogen will come to the first carbon and second hydrogen will come to the second carbon. This reaction is done in the presence of partially deactivated palladized charcoal. It is known as a Lindlar catalyst. It is known as a Lindlar catalyst. It will become, that is one hydrogen will come to here, that is CH2, double bond CH2 will be the reaction from alkynes. Then in the case of beta elimination reaction is a second reaction. It is done in the presence of alcoholic KOH. So for example, if it is CH3 CH2X, it is reacted with the alcoholic KOH. It is done in the beta elimination. You have to know what is meant by beta elimination. In a beta elimination reaction, the halogen will be removed from the alpha carbon, and from the beta carbon, that is the second carbon that is attached to the halogen. So from the beta carbon, the hydrogen is removed, is known as the beta elimination. So from one hydrogen and one halogen will be removed, it will form HX. So it will form HX. So the what will be further, that will be CH2, double bond will be placed CH2 double bond CH2 plus HX. This is the condition of beta elimination reaction. What is the rate of beta elimination reaction? If it is primary, secondary, tertiary, is tertiary greater than secondary greater than primary. If it is chlorine, bromine, iodine, it will be higher for iodine, having higher molecular mass, then bromine, then chlorine will be the nature. Then we are discussing in the case from preparation from alcohol, that is you are given with alcohol. What will happen if it little bit of sulfuric acid is added to my hand? It will undergo dehydration. In the same way, from the sulfuric acid is added to CH3 CH2 OH, that liberation of water will occur, that is the OH, and H from here will be liberated, so it will become CH2 double bond CH2 plus H2O. So now we studied the preparation from alkynes, beta elimination, and from alcohols. So now we studied the geometrical isomers like cis and trans isomers. Cis are in the same side and trans are in the opposite sides. Then we studied the preparation from alkynes, that is the preparation that is done in the presence of linear catalyst, that is partially deactivated palladized charcoal. Then we discussed the beta elimination done in the presence of alcoholic KOH. Then we studied the from alcohols, the reaction is done in the presence of concentrated H2SO4. Now we are discussing about what is Markovnikov's rule and what is meant by anti-Markovnikov's rule. The anti-Markovnikov's rule is also known as Karash effect or peroxide effect. Karash effect or a peroxide effect. First of all, I am discussing about Markovnikov's rule. If it is an unsymmetrical carbon atom, if HCl is added, this will be cut into, there will be 3 carbon and it will be 1 carbon here. So what will happen? The carbon having less number of hydrogen will be attached to the negative one, and the positive one will be attached to the carbon having more number of hydrogen. This is the condition. The carbon having lesser number of hydrogen will be attached to the carbon, in this carbon having less number of hydrogen, and the carbon having more number of hydrogen will be attached to the hydrogen, that is the positive one. So that is chlorine will come here and the hydrogen will become here. So it will be 2-chloro-2-methyl propane will be formed here. Is that clear? So in the case of anti-Markovnikov's rule, the anti-Markovnikov's rule is also known as Karash effect or peroxide effect. This reaction is done in the presence of benzoyl peroxide. Actually, we are using peroxide, organic peroxides. So for example, if this is a reaction reactive with HBr, this is H plus and Br minus. By Markovnikov's rule, this is carbon having less number of hydrogen. This Br should come here. The opposite should be takes place, that is Br should come here and the H would become here. That is known as anti-Markovnikov's rule. So it will form a bromopropane. Is that clear? Now we discussed the Markovnikov's rule and the anti-Markovnikov's rule. So now you have to know, during this oxidation reaction, in the oxidation reaction you are using Bayer's reagent. You have to know what is meant by Bayer's reagent. 1% alkaline KMnO4 is known as the Bayer's reagent. Okay, this Bayer's reagent 1% alkaline KMnO4 is used for oxidation reaction, so it is known as the Bayer's reagent. Now you have to know what is meant by ozonolysis. In this ozonolysis, see here, this is CH3, single bond is CH, double bond CH2 react with the ozone, that is O3. So what will happen? This double bond will remove from here and it will form a ozone here. This is known as ozonide. This structure is known as ozonide. This ozonide is further reactive with the zinc and H2O. So this will form a compound and this will form another compound. It will form CH3CHO, that is ethanol, and that is HCHO. It will form methanol will be formed here. Is that clear? It will form ethanol and methanol. So now we discussed about the case of alkenes. In the case of alkenes, we discussed about the general equation is CnH2n. We discussed about geometrical isomerism. The geometrical isomerism is about but2-ene, that is cis but2-ene and trans but2-ene. In the case of trans but2-ene, the dipole moment will be equal to 0. Is that clear? Then we discussed about the preparation from alkynes and beta elimination and from alcohols. Then we discussed about Markovnikov's rule and anti-Markovnikov's rule. The anti-Markovnikov's rule is known as Karash effect or peroxide effect. And from alkenes, we are using a catalyst is known as linear catalyst. What is meant by linear catalyst? Partially deactivated palladized charcoal is known as a linear catalyst. Then we discussed about the oxidation. The oxidation is done in the presence of alkaline, 1% alkaline alkyne KMnO4. It is known as a Bayer's reagent. Then we discussed about ozonolysis, that is reaction with ozone. So when a double bond react with ozone, this double bond will be removed forming 3 oxygen behind this double bond. It is known as ozonide, that is propanozonide. It is further react with the zinc and H2O. It will become CH3CHO, that is ethanol, and HCHO, that is known as methanol. Okay, now we will discuss the properties regarding with the alkynes. CnH2n-2. This is a general equation of alkyne. Let us go to the preparations of alkyne first from calcium carbide. Now we have a limestone, that is CaCO3 with you. It is heated at a high temperature of 800 degrees Celsius. It will become CaO plus CO2. This CaO react with the coke. It will become CaC2. This is calcium carbide plus carbon monoxide. This calcium carbide react with the water. It will become CaOH twice plus C2H2, where C2H2 is known as the alkyne. Is that clear? This C2H2 is known as alkyne. Okay, that is ethyne. Now you have to look at the preparation, that is physical properties, and the physical properties majorly are colorless, odorless, and it is insoluble in water, and they are soluble in organic solvent. These are the major conditions and reactions about these alkynes. Let us go to the aromatic hydrocarbon. The aromatic hydrocarbon that will have a resonance hybridization. You have to know the one and important thing: when the resonance structure increases, stability also increases. It can be represented like this way, or it can be represented by this way, or it can be represented by this way. That is, when the resonance structure increases, stability also increases. That's the condition. First of all, we are dealing with the preparations of the aromatic compounds. For example, in the case of benzene, you have that is ethyne, that you are prepared. In the case of alkyne, now you got ethyne. This ethyne is undergo polymerization in the presence of hot iron. It will become a benzene. So it can be a conversion reaction from calcium carbonate to benzene. So this is the whole reaction from calcium carbonate. It will become CaO. This CaO react with the C. It will become CaC2. This CaC2 react with the water. It will become C2H2. This C2H2 undergo polymerization reaction. It will form benzene. Is that clear? Now we are undergo decarboxylation reaction. We already studied that decarboxylation reaction is done in the presence of calcium oxide, CaO, and heat. Therefore, you have a benzene ring with the COONA. That is sodium benzoate. It reacts with NaOH in the presence of CaO and heat. That is, this Na and CO and O, that is react together. What all the things react together? This Na, this COO and this O react together. It will become Na2CO3. So the balance thing is H here. This H will be formed here. It will become benzene ring. Benzene ring with the Na2CO3. Is that clear? This is known as the decarboxylation. Next is reduction of phenol. That is, this is phenol. That is benzene ring with the OH is known as phenol. It is reactive with the zinc. It will become benzene plus ZnO. Is the reaction is fine. So now we studied 3 preparations. Let us go to the physical properties of these aromatic compounds. That is, it is colorless with a little bit of aromatic smell. That is, with a nice smell, and the boiling point is directly proportional to molecular weight, that we already studied. And you know about the Huckel's rule. That is only for this aromatic hydrocarbon. The Huckel rule provide 2 rules majorly. That is, it should be follow planarity, and also it should have a 4n plus 2 pi electron. For example, in the case of benzene, see here, this is benzene, where the number of ring, this have only 1 ring. Therefore, instead of n, you have to put 1. That is 4 into 1 plus 2 pi electron. That is 4 plus 2, that is 6 pi electron in benzene. See here, 1 2 3 4 5 6 pi electron in the case of benzene. Is that clear? In the case of we can use naphthalene. In the case of naphthalene we can get like this way. So I am using naphthalene. So in this case of naphthalene, there are 2 rings. So 2 rings we can use the equation, that is 4 into 2 plus 2, that is 8 plus 2, that is 10 pi electron should be there. 10 pi electron. So how will be the 10 pi electron? 1 2 3 4 5 6 7 8 9 10 will be there. That is, it will have a 10 pi electron in the case of naphthalene. Is that clear? This is a method to find the pi electron by using the Huckel's rule. So now we studied what is the condition of alkynes and aromatic compounds. In the case of alkynes, the reaction is CnH2n-2. There you study the different types of preparations and you study the physical properties. Then we studied about the aromatic compounds that will undergo resonance hybridization, where you study 3 steps of preparation. First from that is ethyne, that is undergo polymerization, then decarboxylation by using CaO. Then we undergo reduction of phenol, then we study the physical properties, and then we study the Huckel's rule. Huckel's rule follow planarity and having an equation of 4n+2 pi electron. So do these problems related to anthracene and naphthalene and benzene also. Okay, so let us look at some of the reactions of these hydrocarbons, aromatic hydrocarbons. So in the case of benzene, if this benzene react with chlorine in the presence of anhydrous AlCl3, that is a Friedel-Crafts acylation reaction, so it will become hexachlorobenzene. This is a type of a Friedel-Crafts acylation reaction, because benzene react with this is chlorine in the presence of anhydrous AlCl3. If both these two reactions are reactions of a Friedel-Crafts acylation reaction, it will become benzene hexachlorobenzene. Is that clear? Then see, when the benzene react with the 3Cl2 in the presence of UV, I am writing this reaction together. When you think if it is react with the chlorine, it will be same. No, it will not be same, it will be different. Okay, for that I am doing this reaction together. This is Friedel-Crafts acylation reaction. See here, if the benzene is reactive with the 3Cl2 in the presence of UV, this all the double bond will breaks. We already know this addition reaction, all the double bond will breaks, and it will all the this 6 chlorine will be formed in all the bonds. So it will become benzene hexachloride. Benzene hexachloride. It is also known as a gamaxene. It is also known as a gamaxene. Is that clear? So if it is reactive with the 6Cl2 in the presence of anhydrous AlCl3, is a Friedel-Crafts acylation reaction, it will become hexachlorobenzene. If it is reactive with 3Cl2 in the presence of UV, it is addition reaction, it will become BHC, that is benzene hexachloride or gamaxene. Now we are dealing with the Friedel-Crafts alkylation reaction, that is if the benzene is reactive with the CH3Cl in the presence of anhydrous AlCl3, it will become this CH3 will be takes place into this carbon, it will become toluene plus HCl. It will become toluene plus HCl. Is that clear? See here, if the benzene is reactive with the acetic anhydride, this is known as acetic anhydride in the presence of AlCl3, it will form this COCH3 will be takes place into this carbon. It will become acetophenone plus CH3COOH, that is ethanoic acid. Now it is clear. Now we studied the major preparations related to aromatic hydrocarbons. So in this chapter we studied about alkanes, alkenes, alkynes, aromatic hydrocarbons and their reactions related to aromatic hydrocarbons. So study these reactions very well and also read the textbook very well related to carcinogenicity and toxicity about the benzene rings. Okay, for example, if this is the benzene can cause carcinogen, that is it will be cancer causing, and it will be toxic in nature if it is in different forms. If it is in the naphthalene form or asbestos, these are causing carcinogenic. Okay, so read that portions also very well. Okay.
Bright Education Center, Medical and Engineering Entrance Coaching Center, Hilal area, Doha, Qatar. For further enquiries, contact 306000679.